needs no introduction, as they say. Akshay Venkatesh will speak on orbit method and analysis of automorphic forms.
Okay, thanks for inviting me. I'm sorry I wasn't able to come to more of the conference because unfortunately Stanford's term is still in full swing, and I teach Monday, Wednesday, Friday. Okay, so this is it's a talk about works. It's still being written. It's now almost done with Paul Nelson, and it'll be a bit informal in the sense that the way I present it for this talk is quite different to the paper in an attempt to make it a little more accessible, and I've taken a few liberties with the truth. Okay, so I want to begin by telling you about a problem in the theory of L functions which is not as well known as it should be, I think. So you've probably heard that if any L function has a modular or an automorphic form attached to it. And so, for example, I've written there the modular form that corresponds to the square of the Riemann zeta function. The details of this are not important, okay? But it's some explicit function on the upper half plane. Sigma of n is the number of divisors of n. And it involves a special function, the k-Bessel function. Okay, there's no avoiding it, even for something as simple as the square of zeta. And the way this is related to the zeta function is that when you take its Mellin transform, you get the square of the zeta function back. Strictly, you have to regularize this a little bit in this case, but that's the relationship. And when you do that, you get the, does this thing have a pointer? Does it have a pointer?
Yes. Red button.
Red button. Thanks. Okay. All right. So when you do that, you get the gamma function that has to come along to give you the functional equation. Okay, that's fine. And in this example, that gamma function came from the Mellin transform of the k-Bessel function. And that's not so bad. You can look it up in Gradstein and Rijik, or in this case, you could derive it. The problem comes when you try and do this in higher rank. Okay, so when you do the analog of the computation I just did in higher rank, you encounter integrals like this, but much more complicated. Gradstein and Rijik is completely silent about them. And in fact, so there are various, you encounter integrals like this. Sometimes there doesn't even seem to be an exact formula in terms of gamma functions for them. Sometimes we think there are such formulas, but we don't know how to prove them. So that seems like a pretty serious issue. And I think one reason why it's not better known is that when people were first trying to prove the basic properties of L functions on GLN, they wanted to show that it had an analytic continuation and functional equation. And for that, if you just want to do that, you can sidestep that issue. Okay, so as far as what you might call the standard properties go, you can get around it. But if you want to come back and somehow use this relationship to get information about the L function, then you will have to face this issue in one way or the other. Okay, so it's not really going to be a focus of this talk, but I'll just show you. Here's one of the few general identities we have. This is an identity of which the previous k-Bessel identity is the case n equals 2. It involves the product of two Whittaker functions. So these are really functions on. It doesn't matter if you don't know what a Whittaker function is. I'm just so you have a flavor of. These are really functions on some matrix groups, GLN minus 1 and GLN. But they have enough symmetry that the integrals collapse down to being integrals over n minus 1 real variables. So these are very complicated special functions. I think the only thing I want to say about them is what the word special means. They're special functions in the following sense. if you take this function, it's really a function on gln minus 1, and you translate it around by gln minus 1, it's a group, so you can do that, you will get an irreducible representation. Okay, so these are special in the sense that they generate an irreducible representation of that group. There's some explicit formula for them. It's extremely complicated. And I misspelled. This is a result of Eric Stade, not Stout. And it's proved by sort of long and explicit computation. You get this huge product of gamma functions. Okay, so to summarize, the situation is most of our there are many results of this type where an integral of an automorphic form is an L function times a special function integral. And this is where the basic theory of automorphic L functions comes from, these type of identities. And if you want to use this, you need to know more about the special function integral. Okay, so for example, if you want to exactly evaluate the L function, for instance, there's the various conjectures that values of L functions at certain L functions at integer points should be related to some kind of algebraic quantity, just like the Riemann zeta function at even integers give you even powers of pi. So if you want to access that type of conjecture using these formulas, you need to exactly evaluate the integral. There's really no way around that. And in many, many cases, we're stuck with that. If you want to study the L function analytically, its behavior in some kind of asymptoticals when some parameter is changing, you need to correspondingly evaluate the special function integral asymptotically. Okay, and that's the focus. That's the only thing I'm going to talk about. But I think these problems sort of go together. Like I'm going to talk about the way I'll discuss how to compute this asymptotically. It's very algebraic, and I think the same algebraic structures I hope might be helpful for this other problem of exact evaluation. Okay, but anyway, so I'll talk about how you can estimate these guys, and then at the end, I'll give an application to averaging certain families of L functions. All right, are there any questions? Yeah.
Is this result equivalent with the functional equation with this identity, and if you have this identity, then give an impact to that functional equation?
Say that again?
So the result is equivalent. Like in the eco-functional theory, like when you have a functional equation,
yes.
it's corresponding summation from the equivalent.
Yes. But sorry, I don't quite understand the question still. Sorry. Okay, maybe can we talk about it afterward? Okay, yeah, I want to talk about like these Whittaker functions. No one is really friends with them. So I want to talk about spherical harmonics. And you know, when I think about spherical harmonics, I have these sort of horrible memories from my physics classes of these formulas. But don't worry. All right, so we don't need to know very much about them. So I'm going to give you a toy model of the, rather than talk about the actual special function integrals, we're going to we'll talk about a little toy model with spherical harmonics. And then we'll come back to what we need later. Okay, so whatever spherical harmonics are, they're an orthonormal basis. This is a quick reminder about spherical harmonics. They are an orthonormal basis for the two-sphere. Okay, so the way you make them is like this. You start with L2 of the two-sphere, and first you split it up into irreducible representations of the rotation group. Okay, so the rotation group in R3 spins around the two spheres, so you can. And this is very explicit. Okay, you can write this L2 as the direct sum of spaces V sub L indexed by positive integers L. And V sub L is you take all the homogeneous polynomials of degree L, and you just take the harmonic ones. Harmonic means that they're killed by the Laplacian. those are polynomials in R3, but you can restrict them to the sphere. So that gives you that breaks up L to the 2-sphere, but you want a basis, and these are just some subspaces. So what you do is you break these up further down to get down to one-dimensional things. And the way you do that is you just, for each one of these guys, you can look at how rotation on the z-axis acts, and you break it up into eigenspaces for rotations around the z-axis. Okay, so each one of these VLs, it has a basis called which is called this spherical harmonics YLM, where the M indexes what your eigenvalue is under z-axis rotations. Okay, so here's an example. This is a function of x, y, and z, but restricted to the 2-sphere, it's a spherical harmonic, x plus iy to the L. And okay, all you really need to remember of this is that there are 2 parameters for these spherical harmonics. The L parameter indexes an irreducible representation of the rotation group, and the M parameter is a kind of index within that representation. So it's a finer piece of information. So here's the problem I want to talk about. You take 3 spherical harmonics and you multiply them and you integrate them. Now you could, there's not much point doing 2 because they're orthonormal. This is a graph where I did it a while ago, so I don't quite remember, but I think I fixed 5 of the variables. I think all but the L1 variable, and their values are in several hundred. And then I varied L1, and you can see how this integral behaves. So it has some kind of interesting asymptotic behavior. It has, as you see, it dies outside some range. It has a peak, it has amplitude and phase. And the sort of questions that we have to understand for automorphic forms are kind of more complicated versions of this. So this question has been very extensively studied for a long time. I'll give you references in a second. Yes?
What does M vary from? Minus L to L?
Yes, thanks. Yeah, I should have said that. Minus L to L in steps of 1. Yeah, any other questions?
This shape is like somehow universal, doesn't depend on M function.
I'll tell you what the asymptotic okay, so here's the asymptotic formula. You'll probably be able to guess it from seeing this. Here it is. I think this is the asymptotic for the square. Anyway, it's a complicated formula. Even by using the word similar several times in tiny font, I was unable to fit it here. But let me tell you the history of this. So this has been studied in the physics literature for a very long time. Wigner has a book in the 1950s, I think, called Group Theory and Atomic Spectra, where he writes down, so sorry, just to go back for 1 second, apologies. This thing, as you see, it has an amplitude and a phase. Okay, so the correct asymptotic for the amplitude was already given by Wigner, and it's not, I imagine it was known to other physicists before that, but I don't. And the phase, the more interesting part is the phase. We're actually not going to discuss the phase because it's not relevant for the kind of applications I need. But the more interesting part is the phase. That's due to Ponzano and Regge in 1968. And they didn't, I think, they didn't give any proof, but more or less rigorous derivations were given in the 70s by multiple groups. Schulten and Gordon are chemists, actually. None of these people were mathematicians. Anyway, if you know what the asymptotic is, you can do this just by brute force. It's some sort of oscillating integral, and you can do stationary phase on it. But it's not we would like to have some other way of understanding it, because as when we do this in the context we want for automorphic forms, we'll be doing this on some tremendously big dimensional space, and we'd like some sort of way to guess at the answer. Okay, so I'm going to, there's a very nice paper it's not about exactly the same problem, called classical 6J symbols in the tetrahedron. The thing I wrote down, that integral of 3 spherical harmonics, is called the 3J symbol. Anyway, this paper is from the late 90s, I think. It's a very nice, it's written for mathematicians, and it gives you a very clear picture of the story. So what I want to do, I'm going to sketch how this orbit method of Kirillov can help you with this type of asymptotic problem. Okay, so I have to say a little bit about microlocal analysis. Are there any questions? Okay. So at least my understanding of what the phrase microlocal analysis means on Rn is that you start with a function on Rn, and you want to cut it up into pieces that are, well, beyond localized, they're micro-localized, which means that they are localized and their Fourier transform is also reasonably localized. Okay, so you can't, of course, achieve that the function has compact support and its Fourier transform has compact support, but you could ask that most of the L2 mass of the function is in a small interval, most of the L2 mass of its Fourier transform is in a small interval. And you can achieve that as up to a certain limit, which is the uncertainty principle. Okay, so as you try to squeeze the function, the Fourier transform, you can't squeeze its support beyond a certain limit. So the theory of microlocal analysis gives you effective ways and applications of how to take a function and cut it up into these space frequency localized pieces. What we want to do is something which I could call microlocal analysis on a representation. So here I have a representation of a Lie group, and in the example of spherical harmonics, that group would be the rotation group. And the analog of this is you start with a vector, and I want to cut it into pieces, again, that are localized but in a different sense. They are approximate eigenvectors for the group near the identity. So if you have a group and an irreducible representation, it typically won't have any eigenvectors. That is, a vector won't be an eigenvector for the full group because that would be a sub-representation. But you can pick some sort of small ball around the identity, and you can look for vectors that are kind of approximately scaled linearly by that small ball. So let me give you an example. But that's the kind of thing that I want to do. Okay, so this is the same vector I wrote down earlier, x plus I y to the L. And at least up to a constant. I didn't normalize it correctly, but this is one of the spherical harmonics. So I'm thinking of this as a function on the two-sphere. Okay, not on the complex plane. It's a function of the two-sphere. And this is actually an approximate eigenvector of rotations in the following sense. If you take a rotation matrix and you rotate this function, and I'm going to say this is close to the identity. By that I mean, let's say that its distance to the identity is on the scale of 1 over L. Then I claim when you apply such a group element, actually let me start with an easier. This function is an exact eigenfunction of rotations around the z-axis. Okay, if you rotate it around the z, if you spin it, it just changes by a phase. But it turns out if you sort of go only a distance that's of scale 1 over L, it's actually an approximate eigenvector in all directions. Okay, so it takes a moment's thought to convince yourself of that. But all I mean is that there is some scalar lambda such that, normalized, the distance from GV to lambda V and is little o of 1. Distance, I should have said, is an L2 norm on the sphere. Okay, all the norms here are L2 norms on the sphere. All right, I want to say this a little more precise, in a way that's a little more precise about what the eigenvalue is. So I'll do that next. Are there any questions? Yeah.
So on the previous slide, when you had these sums over alpha, are those finite, countable?
Typically, there'll be infinite sums. Like you sort of something like break up a function into small pieces, and then you break up those into pieces whose Fourier thing is. Yeah. also here, if V is infinite dimensional, this will typically be infinite. Yeah. Any other questions?
Something I don't understand. Let's say like lambda G is 1, let's say. G minus identity is of order 1 over L. So then that operator is of order 1 over L. So I don't understand the scaling. It seems to be O of L of E, right?
Oh, sorry, the scaling, sorry. You're saying it might be better than this?
I mean, if you just let lambda G to be 1, then G minus the distance of G.
No. If you shift this thing by 1 over L around the z-axis, its phase really shifts. It's not true with lambda G is 1.
The statement is there exists a lambda G, right?
Yeah, the statement is there exists a lambda G. I think you're like, if you look at how rotations around the z-axis work, you'll see the vector really does move. So it's not true without the lambda G. Yeah. Okay. Yeah, sorry. Any other questions? Yeah. So I think I should say in relation to that, if you took this ball to be too small, then everything is sort of trivially an approximate eigenvector. So you have to choose the correct scale to make it an interesting concept. And again, there's some parallel to the uncertainty scale. All right, I'm just going to reformulate this in a way that allows me to track exactly what this number is. So for that, I use some coordinates near the identity. So the exponential of a skew-symmetric matrix is a rotation matrix, because so skew-symmetric matrices are the Lie algebra of rotation matrices. So I'm going to use that just to coordinatize this, and if I take a skew-symmetric matrix, I scale it down by L, so I'm at this scale of 1 over L near the identity, then the eigenvalue lambda G, the eigenvalue of this, the approximate eigenvalue is e to the IA. Okay, so you can just check that. All right, so at this point, let me make a definition of what you might, some sort of reasonable notion of a localized vector. So let me just talk you through this. To make the definition cleaner, you could work in a single representation, and then you would need to keep track of error terms. So to make the definition cleaner, I'll look at imagine you have a sequence of vectors in the representations VL when L is getting larger and larger. And I'm going to say that it's localized at the point ABC in R3 when the following holds. If I apply the exponential of this matrix, I apply the exponential of this matrix scaled down by L, then this thing is an approximate eigenvector, and the eigenvalue is indexed by A, B, and C in this way. Okay. So at this point, this turns out to be a definition that's kind of sensible and slightly more interesting than you would expect. For example, here are some properties. If you have any vectors that localize at A, B, and C, it turns out that A squared plus B squared plus C squared has to equal 1. So on the previous slide, I wrote down a family of vectors localizing at 1, 0, 0. But no matter what, any sequence, it has to localize to a point on the two-sphere. This two-sphere, by the way, it's a different two-sphere. This is some two-sphere in a frequency space. And there are many different sequences of vectors that localize at a given point. So realistically, there are different amounts of localization you could demand. You could demand localization right down to the uncertainty scale. This is sort of the weakest amount of localization you could possibly ask for and still reasonably call it localization. So I've just written this. As I said, in a realistic application, you might adapt the amount of localization to what you need. But this it gives you some flavor. All right, so I now want to go back to that spherical harmonics problem and discuss how this might help. Are there any questions? OK.
Yes, what was on the last slide?
This slide.
One just.
Can I send you the slides afterward? All right, so let's go back to this problem. So the point is, I want to get to the point where you see why these things are useful. So we take the spherical harmonic, and let's say we know how to disintegrate it, sort of break it up into a sum or maybe continuously an integral of localized vectors. Okay, so if you can't see, I don't know if there's really a good blackboard to write this, but all right. So this vectors v alpha is going to be localized at some points in R3. I already said that this point has to lie in the unit sphere, but it satisfies a further constraint, and that's because the spherical harmonic is an eigenfunction of z-axis rotation. Okay, so in fact, the alpha, when you decompose the y, L1, M1, all the alphas you get have to lie on the circle of height M1 over L1. Same thing for the other guys. Okay, so you get maybe some picture like this. Okay, where this is M2 over L2, M3 over L3. M3 is negative in this picture. And right, this is beta, gamma. So I've disintegrated all three of the spherical harmonics into localized vectors. The first one indexed by alpha, second one by beta, third one by gamma. And once you do that, you write this integral above as some massive combination of integrals v alpha, v beta, v gamma. Okay, but the point is, these things are all approximate eigenfunctions of group elements near the identity. And the only way these things can be non-zero is if their eigenvalues add up to 0. Okay, it behaves like multiplying 3 oscillating exponentials and integrating it. So the frequency has to be 0. Okay, so it translates into that. And what that tells you is that in this picture, I need to find a vector here, and a vector here, and a vector here, all of which add up to 0. All right, so it's easier to visualize that. All right, so firstly, for that to have a chance of being true, M1 plus M2 plus M3 has to be 0. Sorry, I should have they add up to 0 after rescaling by the L's. And this, I should have imposed this from the start. You need this for that integral to be non-zero. So now I'm going to project these pictures down to the, I'm going to project these onto the xy, onto the sort of xy plane. And what you get is you get 3 circles. Okay, for example, the radius of this circle is something like square root of L1 squared minus M1 squared. And what you're looking for is 3 vectors on these circles that add up to 0. And in other words, if there are solutions, there'll be 2 solutions which are mirror images of one another. Okay, maybe I should draw it like this. You have 3 circles. Oh God. All right, anyway. Yeah, there'll be, all right. It's something like you have 2 vectors of prescribed length, and they have to add up to a vector of prescribed length. And there are 2 different ways for doing that, which sort of look like this. And then the asymptotic is completely determined, the amplitude of that asymptotic is actually completely determined by this picture. So the amplitude you saw earlier is essentially the probability density that when you add a random vector of this length and a random vector of this length, you get a vector of this length. Okay, so that complicated formula there, you can interpret it as some kind of probability density of the likelihood of this picture happening. All right, now this, I think you can turn this into a proof, but you would need to use a notion of localization that's a bit stronger than the one that I had written. All right, so the moral of this is localized vectors. The really key thing is this vanishes for most of them. Okay, so the localized vectors behave very simply with respect to various constructions, and so it's worth your while to write things in terms of them. Are there any questions? But this is not, like this, if you look in Wigner's book, you'll find exactly the same pictures and not the same words, but he has some reasoning that's essentially, he's not using this kind of localized vector language, but he has this clearly something equivalent to this understanding. Okay, now, the point of saying all this was eventually to use it in other contexts. So this notion of localized, it makes sense. It makes sense for any sequence of unitary representations of any group. Okay, all you need is the scale that you say you require vectors to be an approximate eigenvector at some scale. You doesn't need to be finite dimensional either. I just wrote down the definition. That definition requires very little to make sense. It just requires some notion of a norm. So you look at unitary representations that come with an inner product. But that's all. It doesn't matter. It doesn't have to be finite dimensional. And if you look at infinite dimensional representations, it turns out you don't even need to take a sequence of representations. You can just take this fixed infinite dimensional representation and study it at different scales. And you still get, so I could take my previous definition where I had a sequence of vectors in varying representations. I could just, in this infinite dimensional case, it's interesting even to fix one representation and have a sequence of vectors in that, which are becoming localized at, so to speak, higher and higher frequencies. And here's what happens when you do that. Okay, in our previous discussion, the role of this triple ABC, which was somehow indexing the approximate eigenvalue. So this really came from indexing some functional on skew symmetric matrices, and it gets replaced by an element of the dual Lie algebra. So if G is a Lie group, this gets replaced by an element of the dual Lie algebra. And the role of this sphere, I said that if you localize on the sphere, it gets replaced by something called a nilpotent cone. So inside here, there's the cone of nilpotent elements. And if you localize, you have to be nilpotent. The only possible places to localize are nilpotent places. So I'm not explaining why that's true, but it's not very hard to prove. All right, so I'm coming to the how to apply this to automorphic forms. But in order to do our application, we set up a basic calculus that allows us to cut up a vector into localized pieces. And this is just, it's an imitation of, there's this classical theory of pseudo-differential operators that in microlocal analysis. So the way this works here is, if I have a function on G star, and remember that's the sort of space of all possible eigenvalues. For any function on G star, we get an operator that acts on any representation. And the way you should think of this is that, like you're trying to break up vectors into localized vectors, if you take this function to be a bump function that's supported very near 1 point lambda, then this operator, op of f, it sort of projects onto vectors that are localized near lambda. So this is, it's some way of formalizing a systematic way of breaking up vectors into localized ones. This whole picture, I should emphasize, it's not surprising. Okay, the underlying idea here is this orbit method. I haven't mentioned it explicitly so far, but it's due to Kirillov from the 1960s. And Kirillov says that unitary representations of a Lie group are obtained by quantizing conjugacy classes in the dual Lie algebra. So and it's sort of part of the general philosophy of this of quantization that you should have this kind of picture. Maybe no one needed this precise calculus before, but there's no surprise that it exists. It's not something particularly novel. I think, however, Kirillov's emphasis was using this idea to classify representations, but the point is that you can also use it to do computations within representations. In this context, there's one very interesting new thing, which we call microlocal irreducibility. And if I have time, I'll talk about it at the very end. Okay, there's something which is not formal. And if I have, I might get to it at the end. Okay, so now I'm going to talk about the application to families of L functions. Are there any questions? Yeah.
A comment. So Kirillov developed his theory for nilpotent Lie groups, and then it was extended to solvable Lie groups by Urbansky and other people with extra wrinkles. And now it's going to reductive Lie groups.
I think it's been understood for a long time, but as you said, through the work of many people, that Kirillov's theory applies well even to, say, semi-simple and reductive groups. It applies perfectly to nilpotent groups, and it doesn't apply sort of in the same perfect sense, but it tells you a lot also for reductive groups. Yeah, any other, yeah?
So your quantization operator op depends on some scale parameter. If the scale parameter still comes in, it replaces a little Planck's constant?
You can, as with, usually you can set it up with a version of Planck's constant or not. Yeah.
So for example, when you said in an infinite dimensional representation, you would have a parameter, a scale parameter which...
Yes. Yeah. Yeah.
In the toy model, you get any new result?
No. In fact, I don't mean to say the whole toy model thing. I'm not saying anything new. I'm just sort of translating things that were known to physicists 70 years ago. Yeah. I don't mean to emphasize as any, like they didn't say it in the way I did, but you know, they would be extremely bored by my presentation of it, I think. Bored might be too weak a word, actually. Okay, but the point of all this is to have a thing that we can really use. So let me describe. All right, so I have to have a little bit of setup about the automorphic forms before I. So if G is a classical real Lie group, so think general linear group or unitary group, something like that. It has an automorphic, what I call automorphic space attached to it, which is just a quotient of the group by its integer points. And this is the space on which automorphic forms live. Okay, and that's all. We don't need to know any more about it. It's some manifold. An automorphic form is something in L2 of that space. Now, as I said, we're going to try to deduce things about L functions from by representing them as integrals of automorphic forms. So there's a family of identities that are extremely nice in that respect. So there's, for certain pairs of groups, H inside G, H is a subgroup of G, they're both classical groups. You take an automorphic form, capital Phi on the big group, little phi on the small group, and there is conjectured and sometimes proven to be an identity of the following form. You take the automorphic form of the large group, you restrict it down to the small thing, and you integrate one against the other. So you integrate this against this, but one is on a bigger space, so you just restrict it first. When you square that, you're supposed to get the L function, or a central value of an L function, multiplied, as always, by a special function integral. Now, we don't need to know the exact definition of automorphic form, but what is important to us is that, like everything else in this talk, the G translates of this function span an irreducible representation, and the translates of this function span an irreducible representation. Okay, so again, they're special in the sense that they live inside irreducible representations, just like spherical harmonics. In this formula, you have the freedom to move these capital Phi and little phi inside that representation. Okay, you're allowed to move them. The L function doesn't change. Okay, when you move them, this changes and this changes, but the L function is intrinsic and doesn't change. And one of the ways I got interested in this area is there's a very nice paper of Peter Sarnak from the early 1980s where he bounds the second moment of certain L functions for gross in character L functions for imaginary quadratic fields by a very geometric method. And although he doesn't explicitly say it, one way to understand what he does is he's making use of this freedom to change the vectors. Okay, and then maybe 10 or 15 years ago, Bernstein and Reznikov made a much more careful study of this and showed how you can do a lot more. Anyway, it's a very useful thing that you can change these vectors. It also changes the special function integral. And we're going to take advantage of that in a second. This identity, here are the families where this is meant to hold. It's meant to hold for G is GLN, H is GLN minus 1. For unitary, so this is a sort of analogous thing for unitary groups and orthogonal groups. For GLN, this is completely known. It's the classical work of Jacquet, Piatetsky, Shapiro, and Chalaika, which is one of the foundations of the theory of automorphic L functions. Sorry, these two lines are switched. But in the other two cases, oh no, they're not switched. Well, OK, something is. There's a conjecture, the very exact conjecture, which should apply, in fact, uniformly in all cases. And it's been proven in the unitary case under some local assumptions. And it's in low rank, it's known in the orthogonal case. So for various reasons, this seems to be a very nice family to study for analytic applications. It also is algebraically very nice. So any of these three instances. All right, so I'll tell you the theorem, and then we'll talk about how this localized vector thing helps. So here's what we show, assuming the validity of that formula. Okay, so we assume that we're in a setting where we know the truth of this formula. Right, this will take a little bit to unpack. We show the average of this central value of the L function. It's normalized by another L function at 1 is equal to 1/2, which looks a little bit strange. Here, this form capital phi is fixed, and the form little phi essentially varies over all forms whose eigenvalues are in a dilate of a fixed set. Okay, they're Satake parameters. You dilate a fixed set. This 2 to the minus beta is it's a peculiar thing to do with the Arthur conjectures that shows up in the formula. But it should be 2 most of the time. So really this is 1/4 most of the time. So this formula really says the average is really telling you the average of this family is 2. We haven't carefully checked that's compatible with the standard heuristics, but it should be. One of the very nice things about this family, usually when you average a family, you get some various of L functions. You get a product over P. But I think for this one, with this nice weight here, all those factors are 1. Okay, so you really get an integer or rational number. Yeah, it's a product of the two. I didn't write it, but there's a product of both the adjoint L value of capital phi and little phi, which is also what's present. So really, this is the coefficient that shows up in the formula. It so happens it's an L function, but our method doesn't really care it's an L function. It's really about averaging this kind of whatever the coefficient that shows up here is what we average. And in terms of the so I think this family is what's called the edge of convexity, meaning that from this result, you deduce an estimate for each term. If you just throw away all but one term, you can deduce an estimate which is little o of the convexity bound. And the reason it's little o of the convexity bound and that you can't do better than that is essentially because it involves some application of Ratner's theorem on invariant measures, which is ineffective, at least for now. Okay, so this gives you a rather interesting collection of averages of L functions which work in arbitrarily high rank. All right, so but what I want to explain is how this comes from how the localized vector concept helps with that. Are there any questions?
The size of F, is that also weighted with the L1F? Or is it just the size?
No, it's just the size. Yeah, it's this, somehow I think with this term being averaged, all the local factors come out to be 1. So this is what comes out of the formula, but somehow it behaves very pleasantly as well. I suppose you might imagine trying to remove this by putting in local things, but I didn't think about it. All right. So this is just a repeat of the formula, okay, from the 2 slides ago. So what we're going to do is we're going to add this up over little phi. We take an orthonormal basis for little phi, and we add this up. All right, so when you add up this side, you just get the L2 norm of big phi. And on the other side, you get the sum of the families of these the L functions. Okay, so this is rather good. This is the sort of thing we want. And this script I is again complicated, but at least we have some setup that allows us to deal with that now. But the most interesting part of the argument actually is that this idea of localized vectors also allows you to deal with the left-hand side. Okay, and so that's what I want to explain. So the left-hand side is in some sense the most mysterious part in this formula because this phi is an automorphic form, and you really have no understanding of it as a function. Okay, you have no physical understanding or explicit formula, so you have to analyze. You can't hope to directly analyze it. All right, so what we're going to do is we are going to choose I have freedom to choose capital phi. So I'm going to choose it to be a localized vector. Okay, so it's an approximate eigenvector localized at some point indexed by some element in the dual Lie algebra. And again, I'm going to suppress this just to make it a bit clearer to talk about, but really there is a sequence of vectors involved. Okay, so there's a sequence of vectors which are sort of becoming more and more localized after some rescaling. So there's a scale which is changing and a vector which is changing. But just imagine that we're working at one fixed small scale and with one fixed vector for now. All right, so here's how the argument is going to go. I need to analyze this. So let me just, as a picture to have in your mind of yeah, let me show you that. All right, what we're going to do is we're going to show that the measure phi squared, so you have a big space here. This is the sort of automorphic space for G. And sitting inside it, you have a small space, automorphic space for H. Okay? And the way you should think of this capital phi is it's this function which just wiggles like crazy. Okay, it's somehow at high frequency. I'm going to show this function is roughly uniformly distributed on the big space, meaning roughly speaking that its amplitude is approximately constant. And the formal way to say that is the measure that it defines is very close to the uniform measure. Again, the rigorous version of that is there's a sequence, and you're saying that in the limit, it becomes equal to uniform measure. Now, that's at first, it looks like that's not enough because this is some sort of measure 0 subsets, and you can't really deduce any information. But it turns out there's a trick due to Bernstein and Reznikov which allows you to thicken this for free. So once you show that this phi squared, I'll just leave it up here, the volume is approximately the uniform measure on G, then you can deduce everything you need about the integral over the H. All right. So here's how that goes. We claim that this measure, that x should be a g. Okay, this thing that's up there, it's a measure on this space, the automorphic space for g. I claim that it's approximately invariant by the centralizer of lambda. So just to remember, lambda is this point where it is localized at. Lambda is in the dual Lie algebra. All right. So why is that meant to be? I take so G is an element in the group that doesn't move this. Okay, I take an element there, and I apply to the vector phi, and now I get a new vector phi prime, which need not be the same vector, but it's also localized at lambda. All right, so I have these two vectors localized at the same spot, and I would like to know, I would sort of like to think that they had the same measure. That is, I would like to know that whenever you have two vectors localized at the same point lambda, then the measures that they define are approximately equal. That statement, it's certainly not a formality. Okay, there are lots and lots of vectors which look essentially different that are localized at the same point. It seems to be true, and this is a manifestation of this thing which I called microlocal irreducibility earlier. Okay, it roughly means that the representation, an irreducible representation, inherits some form of irreducibility even after you microlocalize it. But we haven't proved it in general, and it turns out we can sidestep it for this application completely. Okay, so what we're going to do is we average over all vectors which are localized at a given point. So I'm going to take this measure, and not just for a single phi, but I just add it up over all the vectors localized at lambda. All right, so if you were, this is not true in any reasonable sense, but if you were to imagine that there were a vector space of vectors that are localized at this lambda, I could just go and add up all those measures over an orthonormal basis of that space. And now when you apply the centralizer of lambda, it just shuffles around the terms in the sum, and that's invariant. Okay, now that doesn't quite make sense, but you can make using the symbol calculus I said earlier, you can make you can put in a weight here, and you can make something that basically substitutes for this. So this, you use a bump function supported near lambda and restrict to vectors that are localized in its support, and then you very slowly shrink its support down to a single point, and you get an invariant measure. This shrinking is sort of slightly more subtle than it sounds. So this whole thing on this slide is somewhat similar to what you see in this quantum ergodicity problem that was studied by originally by Schnirelmann and Colin de Verdier and Zeldich. But it ends in a different way, because here you get a measure not invariant by the geodesic flow, but by a unipotent group. Okay, this turns out to be, in our application, a generic, something like a generic nilpotent matrix, and the centralizer of a generic nilpotent matrix is a unipotent group. And that's, I mean, that's, without that we would be sunk. But Ratner's theorem classifies invariant measures. And so I should have, this was written on the slide, but we impose various local assumptions on the groups G and H. And those local assumptions are designed to facilitate using Ratner's theorem. They eliminate certain unpleasant possibilities. And so using them, you find that this average of mu phis approaches the volume measure. Okay, but the weight, so to speak, I mean, Ratner's theorem is what somehow really bridges the difficult point here. Yeah. Are there any questions? All All right, I'm just going to make a couple of notes on this proof, and then I will stop. So one thing which is tempting to do is to specialize one of the forms to an Eisenstein series. And the reason that is that would convert this central L function to a high moment of one L function. Unfortunately, as it stands, our local constraints, they rule out the case of GLN, for example. So we can't put an Eisenstein series. It's ruled out by the local thing. But it's still interesting to kind of think about what might happen. So because there are meant to be these more complicated weights. Like the number 2 in the sort of answer of 2, which comes out in our theorem, has something to do with the Tamagawa number of an orthogonal or a unitary group. It would be interesting to know, even heuristically, if you specialize something to the Eisenstein case, and you just assume that the Ratner thing worked out, if you can see in any way the right type of answer showing up. Okay, because the advantage of working in high rank is when you put an Eisenstein series on one of the groups, you get sort of a very high power of the other L function. But anyway, as it stands, it doesn't apply to the Eisenstein case. The other thing to note is this centralizer gets, so there's as n gets larger, okay, so these were automorphic forms on GLN or UN or SON, the centralizer gets smaller relative to the group. So the amount of work Ratner's theorem does for you, so to speak, gets larger and larger. In some sense, the problem appears to become more difficult, at least measured by for example, when n is, I don't know, 2 or 3, these, you don't need to use Ratner's theorem. You can prove these things directly. But it seems that from this point of view, this problem seems to be getting harder as the n gets larger. It would be interesting to know if that's the case when you analyze it in other ways. The last thing I want to say, so this is a fairly robust method. So there are other ways which relate averages of L functions to equidistribution, but I think this is different. And you can apply it in contexts where this z of lambda, you would get something quite large. And in that case, you have kind of effective, sometimes we have effective versions of Ratner type theorems. And it would be interesting to see if you could get quantitative results in those cases. All right, so I'm out of time, so I'll stop there. Thanks.
Well, thank you very much. Any questions? Yeah. Why is it enough to localize at nilpotent lambda? It seems to be crucial.
Yeah, it's crucial. The role of nilpotents come because if you take really a representation, you would sort of naturally think that it localizes on its coadjoint, but at infinity, that approximates to nilpotent cone. So the same reason that nilpotent things come up in other similar contexts, I think.
We're talking about real groups. Does any of us have any use of yet?
Yeah, well, that was on my last slide. So there's this thing called microlocal irreducibility, and which I won't discuss. But one point I wanted to make is for p-adic groups, basically all the ideas were Roger Howe, maybe not exactly by that name, but under this title, but worked out microlocal analysis on p-adic groups very beautifully in the 1970s, and where we're sort of hoping to actually transport some ideas back from his. But yes, there's a corresponding picture, but much already done by Roger Howe.
Okay, well, thank you very much once again.